Okay, we're now live. Welcome everyone. Welcome to our 7th feature store from ML Meetup. Today we have amazing speakers. Before we move on to Davor, just want to give a quick reminders that the webinar the Meetup is being recorded, and everyone will receive the recording if you sign up for a new newsletter. So I'll send the link here in the chat after. Feel free to send your questions using the Q&A button. We'll go over the questions at the end of both presentations. With that being said, if you take over, Dapper. I'll take over, Jim.
Yeah, I'm gonna introduce this one this week. Hi, welcome to the 7th meetup. And today we have the pleasure of having Salesforce. So we have Alex Araujo and Weiping Peng. Sorry, Alex, if I dismember that. And then we have Ben Chambers from Kaskada. Natalia, next slide. I think you have the slides. Yeah, so today's meetup, the first talk will be by Alex and Weiping, and they're both principal engineers at Salesforce. And they're going to talk about how they built a feature store for multi-tenant, multi-application environments in Salesforce. And Salesforce, of course, are very well known for the number of models they run in production. So I'm excited to hear about how they feed those models with, contextual features, historical features from a feature store. And then after that, so it'll be at around 30-minute mark, Ben will talk about technologies for time travel with Kaskada. And Ben is the founder and CTO, a co-founder, I should say, and CTO at Kaskada. And then we're going to finish off with Q&A, and I think Davor is going to take the Q&A today. So I think that's it, is it? Or do we have anything else to announce, Natalia? Who are we? We're featurestore.org. I think many of you have been here before. You're welcome to submit new talks. We're open to anybody speaking any topic related to feature stores. So please go ahead and submit a talk or proposal for a talk if you have one. And there is a bit more about the community. Natalia mentioned already, there's a website behind it. There's a Medium publication, and there is the newsletter, which if you subscribe to, you'll get early access to the video for this talk. So without further ado, we have a survey. Are we going to do a survey?
Yeah,
no?
We're doing the survey, so we'll send the link after, so people can.
Yeah, I guess we'll send a link in the chat then, so you can as well, if you want to take the survey now, it'll come after. So we do have an upcoming talk after this one. Databricks are going to talk about their recently released feature store. And I mentioned if anybody else has a proposal, go ahead, please, and go. Now, without further ado, then we'll have the Alex and Weiping, you can go ahead.
All right.
If I can interject for a second, during the talk, please submit any questions. We'll get to the questions at the end using the Q&A button. Try to use the Q&A button, not the chat button. It's kind of easier to organize the questions and things like that. So please, please utilize that, and we'll get to the questions at the end. With that, please take it away.
All right. I'm not a regular user of Zoom, so forgive me if I make mistakes of sharing my screen. Let's see. Zoom. Okay. Sorry. Looks like I have to quit now.
Hey, she's back.
All right. Hopefully I can share my screen this time. Should have done that before. All right. Desktop. Sure. Can you guys all see my screen?
Yes, now we can.
Awesome. Cool. Present. All right. Well, good morning, good day, wherever you are, everybody. Well, thanks, Jim and Ben and Natalia for having us. We're delighted to be here. Our topic today here is feature store for multi-tenants and multi-apps in Salesforce. So quick introduction, myself, Weiping, principal architect in Salesforce for our machine learning platform. And here is my colleague and teammates, Alex. Why don't you do a quick hi?
Hello, everyone. My name is Alex Araujo. I'm a data engineer at Salesforce.
All right. So great topics. So feature store, machine learning, I think it becomes a lot more interesting topics around that, a lot of questions, and how do we go about? So without further ado, let's dive into it. Do you guys see this banner on the right? Can you see the whole screen?
Yes.
Okay, good. Yeah, because my side blocked a little. Okay, so before we dive into Feature Store, because we're particularly talking about Salesforce, I'd like to give us a little quick context about Salesforce's architecture, because that's what we're going to build on, and that's the challenges we have to deal with. So for the context, in the particularly interesting part, it's multi-tenant architecture. So Salesforce, we built, we're a SaaS company, and our architecture is multi-tenant. That's one of the keystones of our architecture. There's a few very important implications to us as machine learning practitioners. So first, being multi-tenant means that data in Salesforce is actually owned by our customer. We do not own them. So being owned by them, that means that we have to get strict approval process to actually get from customer in order to use them. And it also means that we have a strict isolation of our customers from A to B. All of this is to make sure we're protecting the privacy of our customers. And as a SaaS company, the second part of multi-tenancy, it actually also means that we provide, we support extendability. So each one of our customers, they have their own CRM business requirements. So our platform actually offers extendability, so they can tailor their own CRM data model into their own business requirements. As a result of that, each one of our customers' data model, they are very unique. They can be very different from one to another. And of course, this situation doesn't get any better, or for us as machine learning practitioners in Salesforce, is that Salesforce also has been growing. We have integrated with a lot of external system. We also have acquisitions, and the system of data, the notion of data, that definitely grow, and the complexity makes it harder for us. We're not complaining, because it's good to have great business and expanding business. So what's the scale we're talking about? Very quick highlight of it. We take multi-tenancy to a different level. We have over, I don't have the actual exact number, so here is our estimation, at least over. So we have 150,000 custom orgs. They're all hosted on top of our platform. And each one of them has different extendable unique data models. And on the multi-app side, the title started with multi-tenant and multi-apps. So building machine learning application in Salesforce, it also means that we build it once. It has to be able to be extendable to each one of our customers so they can customize. We also require them to be able to build it once and fit into customers' different unique data model. So as of now, we have over 50 of those applications that we call the GA. That means any customer can turn it on and then make customization to fit their needs. Another aspect of this is that we are, for the wide range of customers we cover, we wanted to make sure our customer have the option. So we're committed to build things in a substrate agnostic way. So customer have the choice to go with the infrastructure they want to. So with that context being set, with that context being set, to think about the job of building a machine learning platform. Alex and I, we both are in the team where we're building this machine learning platform in order to support this number of different applications, different teams to be able to build those ML apps. And as quickly, like this many number of teams and this many number of different applications need to build on it, the need of feature store becomes critical. So I think this panel group and also this whole meetup group, we're big fan, and there's a lot of content in the past talked about how feature store can bring benefits into this whole platform to allow us to build ML apps easier. So some of those common benefits, at least from me to categorize, and I see it very clearly for our usage. One is that we enable collaboration. In this whole practicing, I call it ML practitioner, there are different personas. Some people are data engineers, some people are ML engineers, and they are data scientists. And then of course, there's also the traditional software application builder engineers. To having a feature store, it definitely makes those persona be able to focus on different pieces, different area, and have the result to be sharing across and collaborate that way. And a big part, and in fact, I think we sometimes call it ML ops. So operationalize feature generation, that's a very big part. Our data is very unique and can be one to another is different. And having that set of data day in and out, the transaction volume of CRM data is huge. And using those data to generate a feature, it has to be orchestrated, has to be automated. So be able to operationalize, allow us to build the data lineage as need to, and making sure the system is monitorable, observable, and traceable. So that's a huge part for us. And it's almost like once you have it, you cannot go back to think about not having it. Another common part I think we all know about it is that the feature value, once you generate it, you want to make sure the training time and the serving time, it's the same. And computing those can be time consuming. We don't want to compute multiple times and create any inconsistency in that. So with those common benefits, I would say we as a Salesforce, with some of those multi-tenancy contexts I was talking about earlier, it definitely has its own set of requirements and the different type of benefit it actually brings to us. So I'll quickly cover some of that. Well, first is the implication to or requirements for the access model. We talk about the privacy of our customer. They own those data. So feature data and raw data, it has to be extension of it. If you cannot have access to the raw data, you should not be able to have access to the generated feature, or even to begin with to generate. So that permission has to be an extension of that access control. And the second part is actually the implication of the sharing. So when it comes to feature data or feature generation, I would say there's two types of sharing. You can share the result. You can also share the code. And those two are, I would say it's different based on the application type. So we have multiple applications. Quite often one team, they wrangled those data down, able to find out a lot of those very important feature values out, and they can decide, are those applicable to another? So like, for example, we had article recommendation. You figured out a lot of valuable information out from each of those data sets that can be used later on a chatbot application, because chatbot FAQ, you can utilize the same. But then at that point, you could have you have a decision point. Do you share the data, the result of it, or do you share the code? Because those two have two different implications, and be able to set that extension from the earlier access rule on the raw data sets that baked into it. It's something we have to very careful and also baked into the architecture. And don't forget about the GDPR. So I think this is a part a lot of us probably take it for granted, but the amount of work to make sure that has applied, it goes deep into the system. Second portion. So we mentioned earlier, a lot of the data model from each of our customers' data, they can be very unique from one to another. So this is actually achieved by what we call Salesforce metadata. I understand metadata is a term probably kind of overloaded. It depends on which context of people we're talking with. So something interesting, if you're ever interested in jumping into here, this link. The metadata API from Salesforce, it's what's driving each one of our customers to be able to define their own custom objects, define their own customer fields, define their own customer rules, define their Apex triggers and all that stuff. So they can run the whole business logic tailored to their own needs. And that set of APIs gives us a very clear view of what fields they have, what kind of customer object they might have, and what kind of triggers, rules they might have set, workflows. So that set of information, when it comes to machine learning, we have to observe, and we also have to make sure it's baked into our definition. Because when metadata change, it usually implies that the feature generation has to be restarted. And when metadata change, you also wanted to make sure there are versions. So all of those feature generation has to start from the CRUD operation of our metadata change. And with that, downstream system also needs to make sure that set of metadata is baked into the feature lineage definition as well. So that's the second portion. Another part, we actually talked about the enable collaboration earlier, but I think the enable collaboration in Salesforce has even another level of empowering. So our personas here, like business application engineer, they actually were the one traditionally dealing with those entities, those data definition, day in and day out. For Service Cloud people, they understood the case object, they understand all of those, how they can be extended, what are the different type of usage they might be. So that part of the knowledge needs to be able to pass over to the people who's building the machine learning application. Of course, if you just say, hey, delegate this part of the work, and now you do data science and I do business, it's never working that way. And this, I would say, feature store putting into here enables all of these personas to be able to join this collaboration and also observe and also putting their own view into this whole pipeline. And the last part is actually our customer too. I would say our customer, they often know the best of their own. So they should be able to bring their own info. They could even help us labeling things and bring that all goodies into the ends when we're generating those valuable features. Last one is this also enables the application sharing. We talked about the different type of application within the Salesforce. However, they're all based on one set of data, one set of CRM ecosystem. So be able to very clearly define that, having the feature catalog enables the entire observability and also enable the transparency of each teams as well. And another part, actually, this part is an interesting one. We have, within Salesforce, actually, customer grow. So when a company started with a small one, hopefully I can see a lot of audience here, well, your company is going to trend that direction too. You usually start with a small and then probably grow, and some even get into a global situation. And that usually will actually means we will need to move our customer from one region to another. Like for example, a global company, they change their focus of their users from Asia to Europe, then this type of migration happens. When data migration happens, I think a feature value has to move along too. So building a feature store within Salesforce, this is something we also need to pay attention to and support. So yeah, I actually can't see the question or anything because I'm in full screen mode. Anybody want to help me out? Should I pause to answer any question that might be already there, or should I just jump straight over to Alex's section?
Just keep going. We'll grab the questions at the end. Okay. Yeah.
Awesome. Cool. Thanks. So with all that said, I'm actually going to pass over to Alex, my colleague, to jump talking about the architectural portion of it. So Alex, give me a sign. I will help drive the slides.
All right. Next slide. So in order to understand our requirements, we're going to talk about the state of the world before we began researching feature stores. Our data lake before a feature store was a custom cloud-native batch-oriented lake. We use Apache Iceberg as the table format on top of Route cloud storage. And we also have a custom metadata service that speaks Hive Metastore. This allows us to store tenant and feature-specific metadata, as well as metadata about the shape of the data itself. The latter is what allows us to integrate with query engines such as Spark SQL and Trino. We also use Apache Spark for ingestion and data management. Data management includes things like GDPR processing, detailing data sets, compacting data, schema evolution, and data repartition. Data isolation means that every tenant has their own table that stores only their data. And they also explicitly authorize applications to access their data. Of course, they can also revoke access at any time. And in this world, ML users perform data exploration using notebooks against the offline data. And they write model training apps using orchestration service and Apache Spark jobs. Next slide, please. So since data systems have inertia, it was important for us to select a feature store that incrementally added capabilities to our stack, as opposed to requiring a major rewrite. And speaking of reusing data systems, we use another system extensively at Salesforce called Apache Phoenix. In a nutshell, it's a high-performance relational layer on top of HBase. It supports a lot of tenant-specific functionalities, such as tenant data isolation, tenant record and dataset deletion for compliance, and tenant data migration. It also exposes a low latency SQL-based API, which makes it easy to maintain consistency across online and offline tables. And it provides a common interface for inspecting and auditing the data itself. So not having to reinvent those capabilities for feature store was important. On the metadata-driven side of things, we also needed a feature generation service. This service is what allows ingested data to be mapped to tenant-specific metadata to produce tenant-specific features. So for example, an article entity in Salesforce can be stored in different locations. It can have different languages. You can even have custom dictionaries per tenant. So when a raw article record is ingested, we need that tenant-specific metadata to actually generate features that are meaningful to a specific tenant. And of course, tenants also define custom sharing rules, which control which applications have access to their features. So feature store ties tenant metadata together with tenant-specific features for us and provides a common interface for notebooking, training, and inference. So as you can see, all the tenant-specific concerns and existing system components required us to select a feature store that supported all those requirements. When researching feature stores, one project stood out for us because its APIs and architecture seemed to meet, the requirements for specific system interactions, as well as all the functionality that our ML teams needed throughout the data lifecycle. And that system was Feast. Next slide, please. So in a nutshell, why did we choose Feast? One reason is that Feast is open source. This complements the rest of our stack. It allows us to work out in the open with a community of data and ML professionals and benefit from everyone's work. The community is actually active and responsive, which was crucial for us to be able to engage them about a lot of the customizations and pluggability that we needed out of the feature store. Also, the functionality in the code is well organized and well documented, which allows our developers to easily get on board and start contributing, and our users to be able to understand how to use it as well. Feast is also very extensible and pluggable. So as you can see from the previous diagram, we needed something that was easy to integrate with the rest of our stack, and Feast fit that bill pretty well. The last point is that Feast APIs and SDKs are simple and easy to use. When we asked our users what they actually wanted from a feature store, no one said, we need X, Y, and Z data features, SQL capabilities. Everyone pretty much said we need something like Feast. Feast also supported all the languages that we were targeting for ML, such as Python, Java, and Scala. Next slide. That's it.
All right, well, thanks everybody.
Great, thanks very much for the talk. I think we have a time for a question or two. We got one from Abbas Raza, and he asked in the Q&A, so I'll go first with Q&A. There's some in chat as well. Do you request customers' approval for model training? What is the scope of the approval? This is in the context of data.
I can take that one. Actually, in some ways, we are not allowed to talk too much about it. But the good thing is that, yes, the answer is definitely yes. Every single step of our ML process, when it comes to handling with customer data, there is no simple question or doubts that we need all the stuff to be legally signed. So there's a whole process of that. And because of the legal, none of us are lawyers. We probably wouldn't dig too deep into it, but simple answer is absolutely yes.
Great. I have a question then while I'm still here. So what are the next challenges, that you see as being the most important? Data quality, online serving. I mean, what do you see as your next challenges in the feature store space?
Particularly on feature store, I would say there is still quite a bit we haven't finished yet. The sharing rule part, I think it can get tricky, because we talked about the sharing data versus sharing the codes, and between different type of application, it also has to tie back with customers' consents. So that particular area, to bake that fully in, it's non-trivial. And I think having this universal governance rule, it's a dream for us to be able to achieve that, but because of how diversified the data is and how our entire CRM ecosystem will be, and it's growing faster than what we can catch up for. So that's somewhere we have to spend a lot more efforts to make sure, we build something, build it right, and possibly be able to extend to share with other area too. Because I would say data, feature data, it applies to the entire data processing pipeline too.
Okay, great. We have a few more questions appearing now. Siddharth has a question about how with Feast, how are you handling querying with multiple primary keys? And then a second question, is this scalable?
Alex, would you take that, or I can? All right, thanks.
So the store that we chose actually performs really well with batches of primary keys, and it scales relatively well for us. It also supports range scans efficiently, which Feast currently doesn't support. So that's something that we might explore with the Feast community down the road to see if there's a way where we can
do you
expose some sort of.
Do you have batching as well, or do you have batching as well?
Yeah. So the Feast API is actually batch based. You get a batch of primary keys, right, and load them all at once. And, there's some other functionality that happens after you load the keys, but in terms of scalability of that particular access pattern, it scales really well on top of our key value store, which is HBase. We also try to protect the service and set same limits so that one application doesn't, consume a disproportionate amount of resources or load much more data than another application. So there's some limits that we set in place as well internally to sort of protect the service in case of hotspots. I wouldn't say abuse. Yeah. Let's call them hotspots. That's a good word.
Another question from Yuang. Are you on Feast 09 or 010?
So currently we are on 09.
And what's your opinion on the latest release of Feast?
So the latest release of Feast is a bit of a departure from 09. So we are actively working with the community on how we actually get back to convergence, and we have a reasonable plan for that. There's some decisions that need to be made on the API itself. One of them is, do you completely deprecate the feature table API, which is what's in 09, in favor of the feature view API? Do you support both? If so, are they strict supersets of each other? Are they, how do we avoid confusion in terms of users adopting those APIs? So that's going to be one of the challenges that we'll have to tackle once we upgrade to 0.10 or later.
Charna Parkey, within an individual global customer account, how can you prevent data transfer between regions with a feature store that shares data? So the EU to the US and back again.
I can jump into on that one. So actually for us, each of our customer, they have a very specific dedicated region. Yes, you are a global customer, but when it comes to processing data, we don't do the distributed data processing and then aggregate later. So we do choose whichever region that's the most common representation, and then we'll put there instead.
Great. I think that's it. We're done for questions for the moment. So thanks very much again, Weiping and Alex. Looking forward to talking to you again and on your journey in the feature stores and how it progresses. And with that, we'll switch over to Ben Chambers, CTO and co-founder of Kaskada. And Ben's going to talk a bit about time travel, I believe, and not Doctor Who, my guess is.
Let's see if I can get this. All right, can everybody see that? I assume that's working.
Yes.
Yeah, we're good. We're
All right, perfect. Hi, everyone. I am Ben Chambers, CTO and co-founder at Kaskada. We've been working on the data processing necessary for creating machine learning models from event-based data. Like Jim mentioned, this is requiring time travel, so that's what I'll be talking about. Before Kaskada, I worked on Apache Beam, where I built the first version of windowing and triggers for the unified model of batch and streaming. I also did some work on the user-defined functions within the Beam Java SDK. So with that, let's talk some more about event-based models from the data engineering perspective. In this presentation, you'll see why time travel is needed to create event-based models, and I'll discuss how existing systems don't really make this easy. And finally, I'll talk about how you can provide time travel and make it possible to predict the future. So let's start by talking about why time travel is necessary. Everyone wants to predict the future. Data scientists will likely need a feature store so they can collaborate and share features, access to the event-based data stored in your data lake, and a data processing system that allows them to easily create features and train models. If they're not already using event-based data, they should be. The only constant is change, and understanding how things have changed enables predicting how things will change. So this all sounds easy, right? Just give them a feature store and everybody can use that. But what if that's not the hardest part? What if the difficulty lies in understanding how things change over time? To predict the future, the model must be trained on the past. And time travel is important because it's about understanding the past. To do this easily, you'll need to provide tools that support time travel. Let's look at a few examples about what this means. In this first example, you want to train a model that predicts whether a user will quit next month. The entity that we'll be making predictions about is the user. So we see a training example here for user 1 with the prediction time, which is when we want the model to make predictions. In this case, the start of the month, so March 1st. And a label time, which is when the result that we want the model to predict is known. So this is the future that the model will predict. In this example, it's, at the end of April, we can determine whether or not user 1 quit in the month after March. It is important to keep these 2 points in time separate. The model should only be trained on information available when we intend to use it. Using information that isn't available at the prediction time would lead to leakage, and models that may perform well in testing but fail in production. For example, if this training example included a feature that indicated the user had quit, because we know that by the end of April when we're training our model, the model would do very well in validation, but it would fail in production when that information wasn't available. But leakage often isn't that obvious. Consider a feature recording daily logged in activity. A user who has quit would have no activity compared to users that haven't. So it's not as simple as whether or not the result leaks. It's any information from after the prediction time can lead to leakage. We can actually create many training examples from one data set, possibly multiple training examples from each user. So here we see 2 more training examples with prediction times at March 1st and April 1st, and labels at the end of April and the end of May. If your data scientists knew up front the times that they would be making predictions, so in this case, the beginning of each month, this would generally be enough, but they often don't know that. Let's look at an example with data-dependent times. Here we have a bunch of house listings and the eventual sales details. We want to predict what a house will eventually sell for when it is listed. The prediction time is the time of the listing event. In the first example here, we see the prediction time is January 10th when house 1 was listed. The label time again is when the sale occurs, and the target value is the sale price. So here we can label the first training example on April 15th when that house sells. The prediction and label times for each training example depend on the data, when the house was listed and when it sold. In addition, the times are different for each training example. House 1 was listed and sold at different times than house 2. We'll see that these dependencies and differences make creating the training data more difficult. One last example. In this case, we're trying to predict 5 hours before a flight is scheduled to depart, whether it will depart on time. The prediction time will be 5 hours before the flight is scheduled to depart, and the label time will be when it was scheduled to depart. In both of these examples, the flights themselves were scheduled very early in January, and they were scheduled to depart sometime in July. This is data dependent in that we need to look at the data to figure out when the prediction time and label time should occur. But unlike the house sales, it actually uses a different event, the scheduled event that occurred much earlier. We'd also like to join the information about the flight with information about the airport and other flights at the same time. We need this join to be temporally correct, which is an easy requirement to miss. And when it arises, it may set your project back months. The main takeaway from these examples is that to accurately create models from event-based data, we need to create training examples that are representative of the times that the model is intended to predict. This needs to be easy to adjust so that different models can be developed and tested. There are several capabilities that we identified that we would need to provide. The ability to create separate prediction and label times for each example. This relates directly to how the model will be used, making a prediction at one point in time about values that aren't known until some later point in time. The ability to have different times for each training example. This is necessary because the model will be asked to make predictions at different times, so we need to train it at different times. The ability to choose the times for those training examples based on the data. This is necessary because it may be impossible to know without looking at the data when predictions will be needed. For instance, we may need to look at when a house is listed or when a flight was scheduled to depart. And finally, the ability to compute correct values for each point in time, even when performing joins. Anytime data is joined, there is the risk of leaking information from the future that won't be available when the model needs to make a prediction. For example, joining with the content of a relational database might indicate a user has quit with the latest information, which would make it easy for a model to cheat when being trained to predict churn. Even if it's not so blatant, their logged in activity has likely dropped. The ability to work with historic data to produce training examples. This is also necessary to backfill new features so they are available for serving. The ability to update features in something similar to real time for serving the latest results. And finally, all of this needs to be provided in a way that is easy to use and iterate on. Because in addition to change, another constant is that the first model won't be perfect, and the faster you can make changes and iterate, the better the models will be. Now that we understand what is necessary for creating event-based models, let's look at how it can be provided with existing systems. One naive strategy we've seen used is to just issue a separate query or create a separate data frame for each point in time. This is a natural idea that can provide correct results, and we've seen it work early on for projects. So for instance, you go to Python and you say for each time that you want to make a prediction at, create a query limited to the events that happened before. And then execute your query, compute all of your features over that input subset, and then output the features. But this approach has one huge flaw. To produce thousands or millions of training examples, it issues thousands or millions of queries. We've seen this lead to hours or days to create training examples, even on relatively small amounts of data. As a result, it is impractical to create training data using multiple queries. If you use multiple queries, you may be able to solve these problems and create models for a while, but you'll likely need to start over at some point. Let's look at using batch processing systems like Pandas or Apache Spark. These make it easy to work with historic data. They emphasize aggregating the input to produce the final values. This emphasis on unordered data makes it difficult to compute at specific times. Providing time travel is generally impractical. You may be able to write a pipeline and group by entity and sort by time and truncate the data using windowing or some other mechanism. But such a system would not provide correct temporal joins. If you looked up values from the final values computed, you would get those final values. Additionally, doing so efficiently requires a deep understanding of the framework to make sure it doesn't excessively resort or reshuffle the data. And this need for expertise limits iteration. So batch processing does not make time travel easy. Next, what if you used snapshots or periodically wrote to a feature store? You could either run one instance of the batch job for each snapshot, or you could write a pipeline that computes all of the snapshots in one execution. Either way, this can provide a form of time travel, assuming that the granularity of your snapshots is sufficient. But there are a variety of problems introduced by that limited granularity. If you have daily snapshots like this example, the feature values for predictions made during the day may not correlate with the features in the snapshot, which would make the model less accurate when actually used. Additionally, the snapshots may lead to incorrectly assuming that the data from that snapshot is available because it was available when the training was run, even though the pipeline to produce that snapshot would not have run when the predictions are actually being made. So just snapshotting feature values to a feature store also doesn't make it easy to support precise kind of point-in-time time travel. Stream processing systems like Apache Flink are another reasonable choice. They make it easy to subscribe to the stream of events and produce the current values. The ordered processing enables computing the values at the current time, and which makes it easy to support the real-time serving needs. But combining values from separate times will require custom stateful operators. And it's difficult to use the stream processing system to create training examples from historic data. Additionally, there's likely a complexity involved to initialize new features from that historic information. You can think of this as kind of how do you backfill or start the pipeline when you add new features. So if you just use stream processing, it also won't make time travel easy. Finally, what if we combined two of the approaches we've already looked at, using snapshots for historic data and streaming to maintain the current values? This may provide some forms of time travel, but it has the same granularity problems that we discussed for snapshots. But by adding streaming, we made it possible to support real-time feature values. However, the big limitation here is that it may require that the features are written twice, once for each system, which makes it difficult to move models from training to production and makes it difficult to iterate. So even combining these two approaches doesn't make time travel easier. In fact, you may just have to solve many of the same problems twice. To summarize, time travel is hard with the existing systems. These systems don't really address it. At best, they provide time travel with limited granularity or require expertise to create pipelines that aren't easy to iterate on. But time travel is possible. So let's talk about a general strategy for handling time travel. This is a high-level overview of the steps that you could take to provide time travel. First, it's important to think about the whole system. Use an event stream to serve the latest features and store historic data for creating training examples and backfilling new features for serving. Because the historic data is potentially large, process it using multiple partitions like in batch processing. Within each partition, process events in order, like a streaming pipeline. As you go, check to see if each time should be a prediction or label time for a training example. We can see in the image that because you're processing events in order, if you're interested in the value at time t, when you get there, you will have incorporated all of the events up to that point in time and have the correct value. Ordered processing like this is difficult to do in batch systems, which tend to focus on the final answers and assume order doesn't matter. Try to compute all of the features without shuffling or processing any event more than necessary. And finally, make this easy to change, because as we've noted, you'll need to iterate on the data to improve the model, and that may require changing how prediction or label times are selected. Once you've identified a prediction time, you'll have the necessary feature values for that point. But to create a complete training example, you'll need to hold on to them until you reach the label time so that you can emit, both the prediction values and the target value that you want the model to predict. If you're using streaming, this would require writing custom stateful operators. If you're using batch, it would require thinking about how to join these values. Next, be very careful with temporal join. As we discussed on the flight information example, you'll need to do joins in a way that is correct for the point in time that you're trying to make the prediction. Your project may go 6 months or a year without the joins being necessary, but at some point, data scientists will need to join values from other entities or even other systems in order to make the model better. And they'll need those results to be correct and without leakage. This join is particularly difficult to do while preserving the partitioned execution and ordering requirements that we've talked about, because it introduces dependencies between features and they're no longer embarrassingly parallel. If you're not careful, this will lead to deadlock. Think carefully about how to separate your computations and schedule them to avoid this. And you'll likely need to redo this thinking every time a feature is added. Finally, after all of that, you'll have a system that provides time travel. You and your data scientists can easily create training examples with separate prediction and label times without leakage. And you can create models that predict the future. Now you'll need to figure out how to serve the same feature computations in real time for deploying the model, while ensuring that the values are consistent between training and production. This will generally require some form of incremental computation. You can think about storing enough state after processing the past events so that you can pick up where you left off and just incorporate the new events. If you're lucky, you can add this to the system that we just described. If you're not, you'll need to build another system to provide real-time serving. There you have it, the 5 simple steps to building a system that makes it easy to train models that predict the future. Thinking about the whole system, the stream, lake, and how you compute features. Making sure that you process events in order and partitioned by entity. Making sure that values from the prediction time can travel forward to the label time. Being careful to support correct temporal joins, and being able to incrementalize that computation so that you can serve them in real time. Your data scientists need time travel to create models that predict the future, but it is hard to predict with existing systems. You can provide time travel if you take these steps. You could also provide it today with Kaskada. Time travel and feature engineering are big topics. If you're interested in talking about these, we'd love to hear about your problems.
All right, thank you, Ben. I think this was a great talk. Let's start with a few questions. I think we have one question for the Salesforce team, and I think this one's for Alex that I think Jim missed earlier, which is how do you do backfill of features if the code changed in Feast? Alex?
So we actually don't do any backfill of features. What we do is we update new features to include the new computations, and the old ones all retain the old values. That helps with having to go back to a previous snapshot to see what the values were then, as opposed to
So
train the snapshot. Sorry.
You never change the feature, you always add a feature, and then how do you backfill for the new feature then?
Was that a separate question or the same question? I'm
trying to just make sure it's fully answered. I don't know, I'm just trying to make sure that Dino gets the full answer. Yeah, so the answer is we don't do backfill of previous features. We only set the value based on the current code for new features moving forward. All right.
Yeah, I would add a little bit is that we have to do versioning. So each set, like say, for example, if the change is caused by metadata change, that will trigger the process to run. And then that has to map to the exact version of that metadata. So you know exactly which one to use when it comes to training and serving time.
All right. Next question is for Ben. Yu Cheng asks, how do we time travel slowly, changing data, such as demographic profile data, which doesn't change so often like time series events, but is not constant value either? So this is like a question for slowly changing data and time travel, like profile information, not like click stream or transaction stream or something like that.
Yeah, I mean, it's a good question. I think, if you can handle time travel for fast changing data, you can handle time travel for slow changing data. But I think one of the interesting aspects of this question is talking about data that may traditionally be in a relational database. And, kind of what we mentioned is that even that data can change. And anytime that you are joining your events with that relational data, you'll want to, instead of kind of having just the values, have kind of the change log. And there are a variety of systems like change data capture that you can feed in. And so you can join your kind of user event data with information about when their demographics changed. And so you'll basically be able to say, training on those values as they change over time.
All right. And then Anonymous Attendee asks, are there any existing technologies that enable for temporal joins?
There are technologies that enable joins. I think doing temporal joins is often difficult. The only thing that we've seen kind of that isn't kind of time travel and time aware joins is kind of limiting your data set to the point in time that you want to make the prediction at, and computing both the values and the values you want to join with at that time. But that's not really kind of a generally tractable solution.
Right, and I can also kind of chime in here, kind of, we've worked on Beam, and Beam, for example, does not solve this, not even closely. Right, like these types of joins in Beam are best effort, and the runner and the execution engine don't guarantee you correctness of data, but kind of just a best effort type of thing will give you something to join that is reasonably fresh, but we actually don't provide any kind of correctness guarantees to be able to do temporal joins, and that's the answer for Beam. It's very likely answer in other systems too. I don't know for a fact, but like I suspect it is. So these are types of joins that generally existing systems can't do. Anyhow, that was the last question, as far as I see in the Q&A and chat. So to wrap it up for today, I'd like to thank Weiping and Alex and Ben for sharing a part of this Tuesday with us and sharing their knowledge and experience with the community. We will see you in a couple of weeks when we will have Databricks talks and more to come. So thank you for attending, and see you all soon.
Thanks, everyone. Remember to sign up for the newsletter to receive early access to the video recording. And have a great day, everyone. Thanks.
Thanks.
Thanks.